Hello, my dear students, and welcome to a quick screencast of our last subject area for this particular unit on measurement. And this particular unit is on density. So I will start by telling you that density is often confused with weight or mass, and we think of things like boats floating or helium balloons floating in the air, other things falling and other things sinking, and buoyancy and density are definitely related. And what density is not so much the mass of an object, but it is specifically a ratio of the mass to the volume of an object. And that is something that can be determined whether an object floats or sinks in water. But there are other factors such as volume displaced and the like. But what determines the density of a substance, as I said, is the ratio of the mass to the volume. And for those mathematically inclined, if you have a plot of the mass on the y-axis, where we have mass in grams typically plotted, and on the x-axis or the horizontal axis or the ordinate, we have volume plotted. If you do this particular plot and you get some numbers that give you an approximate straight line going through 0, you will find that the slope is equal to the density. And that makes sense, right? Because what is slope but the rise or the change in y divided by the run or the change in x. So I'm not sure if we'll do it or not, but I do have a lab where we weigh an object. It's actually a penny, and the number of pennies, we weigh 5, 10, 15, 20, 25 pennies, and we calculate their volume because it's hard to calculate the volume of one, and we weigh them or mass them and determine their mass. And then we take those values and put them into our TI-84s to determine the slope of the resulting line, and that gives us the density. But you don't need to do multiple measurements for any one measurement of an object, determining its mass and dividing that mass by its volume, you get density. So let's talk about some examples. Here's a few items. 10 grams of lithium. 10 grams of lithium would have a volume of, I can't quite see that value, 19 cubic centimeters. Water, of course, 10 grams would have 10 cubic centimeters of volume, or 10 milliliters. And a 10-gram sample of lead would have a volume less than 1 milliliter. It's more than 10 times denser than water. And so each of these samples weighs the same, masses out the same, but of course the volumes are greatly different. Lithium, by the way, is a metal that floats. It's kind of interesting. And Star Trek fans, there's no such thing as dilithium in our current chemical inventory. So, density is something that you can look up in a table. If you're using your Flynn scientific table of the elements, you will see it. It's a green value on the front page of it. And it's listed for all of these elements, and most of the elements listed in grams per cubic centimeter or grams per ml. And you see extremely dense substances such as gold. I've heard that a brick of gold is surprisingly heavy. I've lifted bricks of lead and they are surprisingly heavy. I'd love to try it with gold someday. If one of you gets rich, please donate a gold bar to me. I will use it purely in the classroom for teaching. But as you can see, water has a density of 1 gram per cubic centimeter. And that is at 4 degrees, but 20 degrees C is okay as well. They qualified here, 4 degrees, so they're okay. And as you can see, ice is about 90% the density of water, so it floats 92% better, more appropriately. And you can see some things, but when you look at the gases, you'll see that our units change. So here's units. We can do conversions and we can put it in grams per milliliter, but the gases are typically reported in grams per liter because it gives us units that are easier to work with and I think easier to comprehend. Those units range, of course, from 1.2 grams per liter for air. And if you look, you'll see carbon dioxide is considerably heavier. Chlorine gas, which stays near the ground, much heavier, falls down into the trenches when it was used as a chemical warfare agent. And you'll see that, for example, hydrogen and helium have very low densities there. So that should explain some phenomena to you. So we see the applications of density all the time. Oil floats on water. Corn oil floats on corn syrup, which is a lot of sugar dissolved in water. And that increases the density of the water so that water would float on corn, not on corn syrup, whereas the corn oil would float on it. You can make things with 3, 4, and 5 layers by exploiting the density of different liquids. So we will be dealing with density and measuring density in a lab for Virtual Monday. And that will bring an end to our subject area. We'll do another lab or two and then have a test next Friday. So how does a change in temperature affect density? Well, here's something you should know. You probably know it already or have experienced it. When objects heat up, in general, they expand. So as temperature rises, the volume of substances expand, of an object expands, and of course the mass, which can neither be created nor destroyed, and we have that law of conservation of mass, the mass remains the same. So if density is equal to mass over volume, and if the volume increases, if our denominator increases, it means that our density can only decrease as the volume increases. So in general, with one notable exception, and that being water, objects, as they heat up, their density decreases. You may have heard that hot air rises. And that's true because as the heat warms the air, it decreases its density, so it will rise above the colder, denser air. Heat does not rise, okay? Heat can only flow from hot to cold, and it, you know, heat doesn't rise, however, hot air does. So, here it says density decreases as temperature increases. So, if we look at some sample problems real fast and get through this, if I have a copper penny and it weighs 3.1 grams, that's its mass, and it has a volume of about a third of a centimeter, 0.35 cubic centimeters or milliliters, then my density, which equals mass over volume, is going to equal to 3.1 gram per 0.35 cubic centimeters, and that will give you your density in grams per cubic centimeter or grams per milliliter, those being the same thing. If you do plug in the numbers, you will see that you get an answer like this in your calculator, 8.8571. But each of our numbers that we worked with had 2 sig figs in them, so we need to have our answer with 2 sig figs, and we would round to the nearest digit and get 8.9 grams per cubic centimeter for our density of copper. And we'll go ahead and do this in the lab next week. So, once again, I'm going through the notes that have already been posted. These are available for you as a PowerPoint to view online. You don't have to go through this whole thing to find your answers for the section review and watch the movie over. Everything is available, like I say, online in the course stream. Silver, of course, is a very dense substance. If you have a bar, it weighs 68 grams and has a volume of 6.48 cubic centimeters. You would simply divide the 68 grams by 6.48 and you'd get a density of a little over 10. You can do the math. It's very simple. So, here's a problem. We have a coin has a mass of 14 grams and the density of silver is 10.5 grams, and it wants to know the volume. So if density is equal to mass over volume, what I can do is rearrange this equation so that multiply both sides by V. That would give me dV over here. And then divide both sides by D. It would bring my D back over here to the denominator. And so I can use this equation and rearrange to solve for different values. So that in this case, my volume would be equal to the mass, 14 grams, divided by my density, which is 10.5 grams per cubic centimeter. Okay, the grams cancel, and the cubic centimeters comes up for the volume units for my result, because here the denominator in the denominator becomes the numerator. You may have heard that in your math classes. I hope you have. The denominator of the denominator is the numerator. So this value for cubic centimeters comes up to my answer. So if you have a calculator, I don't have one right now, 14 divided by 10.5 will give you your numerical value, or I will just scroll ahead to that value. And here we have it, 14 grams times our conversion factor, our 10.5 grams of silver corresponds to 1 cubic centimeter of silver. And what they've done is rearranged this density so that their grams of silver cancel, and they get 1.3 cubic centimeters of silver. So, just quickly, some sample test questions. If you have 50 milliliters of corn syrup and it has a mass of 68 grams, if you want to solve for the density, all you would do is divide your density is equal to mass over volume, and you would divide your mass by your volume, and rounding appropriately, you would get a value or an answer of 1.37. Okay, see if I can get into the next slide. There we go. And here's another good question, one I hope you can almost do in your head. What's the volume of pure gold coin that has a mass of 38.6 grams? Well, volume, as we showed, was by rearranging our equation, mass divided by density. That's an M, but it's the best I can do. And of course, 38.6 divided by 19.3. I don't know if you can see that, but that would give you 2 cubic centimeters, since one is twice the other. And as temperature increases, density tends to decrease and things become lighter. And thank you for sitting through this. I know these can be a little agonizing, but I want to stop and point out what's essential in these subject areas, and we will try to keep them as short, and I'll try to talk as quickly as I can and still be understandable. So, thank you for bearing with me. Please use this to answer the accompanying questions in the section review. For this section, it's quite short, and I will have some labs for you next week and a test over measurements next week, all ready for you and ready for you for Virtual Monday. And in the meantime, stay safe, and I will see you in the next video.